Okay, so good morning, everyone. Um, we have come to an important demarcation place here in our course on cosmology. Remember, the working definition we've had for cosmology is that it is the study of the overall structure and evolution of the universe on its largest scale. We're not concerned with the solar system and the planets. We're not concerned with the life cycle of stars, any kind of detail. All very important topics of astronomy, but in cosmology, we're only looking at and concerned with the biggest pictures. And so we pretty much finished, our introduction to the first part of cosmology. That is the overall structure, the overall processes that make up the universe today. Certainly the most important single one, the one that you always want to start out with, is the fact that the universe is expanding, discovered by Hubble in 1929. That is the overall biggest thing that you can say about the universe on its largest scale. So when you get to the second part of what cosmology is about, the evolution of the universe in time, if the universe wasn't changing, if it wasn't evolving, if it was static, eternally the same, which is what all scientists virtually believed up until the time of Hubble, the whole tradition of science in the Western world, one of its tenets was that the universe was more or less the same, no matter what time you looked, even if there was some kind of a creation story involved with it. Once that story kind of was over and the universe was then made, it would then be pretty much static and unchanging. But we now know that in fact the universe is expanding. That is, that the universe is bigger today than it was yesterday, and that was bigger than it was the day before. So the universe is evolving, and so we do have something to say about the evolution of the universe. How did it get to be as we understand it today, as we've spent these classes talking about its structure, its composition, for example, with dark matter and dark energy and the proportion of those compared to normal atoms and all the rest, the flatness of the geometry of the universe, et cetera, et cetera. The great surveys of what the web of these filaments and voids of the galaxy structures are. The other question of cosmology is, how did we get here? How did this come to be? And we're going to be looking today as an overview of the most important theory for that, the Big Bang model, but it has a more specific name because there are many theories which start with a Big Bang. We're going to be talking about the standard one, the one that most astronomers, astrophysicists, physicists uh, feel is the best story we have right now. It's a complicated story. It's a long story. It's a long universe, about 13.7, 13.8 billion years since this Big Bang, since its beginning, where everything came from a tiny area or volume, smaller than an atom in its beginning. It's been a long time in this evolution, and so you can imagine it's a rather complex story. So for today, what we want to do, our goal for today, is to introduce the Big Bang model at its highest level. And then next week, we'll start to look at some of its very important components, um, and why some of the things, some of the components of the model are there. What is it that, what purpose does it, is it serving? We'll get to that next week. And finally, in the last week, we'll look at some of the questions and problems that exist in this standard model and what's possibly being looked at as an alternative to this, again, the standard model that we now have of the Big Bang. So that's where we'll be going for our last three classes, studying the current model of the Big Bang, its strengths, and then its weaknesses, its open questions. I want to start with the idea of redshift, one of the most fundamental ideas in cosmology. We've seen it in some of our pictures that we've had before. Here's one that we've used in one of our previous presentations of the structure, the overall structure of the universe. And you can see that here we're looking out at further and further distances, out to about 4 billion light years in this particular survey, the 2DF survey. And on the other side, there's a scale of redshifts. So apparently redshifts are associated with distances. And this idea of redshift is fundamental. And we want to take a look at it more carefully and see just what is this relationship between distance and redshift. And we'll see that we can learn a few interesting things about the universe by looking carefully at this idea of redshift. We know conceptually what we mean by the redshift. That is that the wavelengths of light are being stretched out. They're being stretched towards the red side of the spectrum. That's where the red comes from. The wavelengths are getting longer, and the longest visible wavelengths are in the red, and so we call it a red shift. It's not that these wavelengths are all in the red, not at all. As they get longer and longer, they'll go into the infrared, the microwave, and even into the radio wave. We just call it a red shift because that's the direction on the spectrum line that these wavelengths are shifting towards. Another interesting thing about this is an astronomy picture of the day that I picked out at the time. I forget what presentation this first came in, maybe the second one on the structure of the universe. But it's interesting what I've highlighted here in red, that although the distribution of galaxies appears nearly uniform on the largest scale, which is one of our fundamental ideas, this is the cosmological principle, that at its largest scale, looking at it from this furthest way back, from a God point of view, the universe is essentially homogeneous and isotropic. It's basically the same everywhere. No matter what direction you looked at from any place in it, it would look essentially the same at this largest scale. So although it appears uniform on the largest scale, waves of galaxies are discernible, extending up to this 100 million light years here. So if you look at this, the blue and the white, you do get kind of a wavy kind of nature to the distribution, the thicknesses where the galaxies are and where they aren't. It does have kind of a wave kind of idea to it, and that's an idea that we'll be coming back to. Here's another picture which we've used before, where again we have distance on one scale and a equivalent redshift distance on the other. So clearly redshifts and distances are very much related. They're used virtually synonymously in cosmology, and we want to understand what this redshift is. Clearly it's a number. It's not just a concept, but it's actually a number, and that number can be associated with distance. These distances you can see are in millions of parsecs, and so remember that can be translated into light years by multiplying by about 3.2. So a million, 1,000 million parsecs would be a billion parsecs, and that would be 3.2 billion light years. And I think we took a look at this at the time to look at the Great Sloan Great Wall. Sloan named after the Sloan survey, which is just completing up actually this year, 20-year survey of the galaxies, looking further and further and further back. And this was from an early result of the Sloan survey, looks like from 2003, where the Great Wall, Sloan Wall, was discovered, one of the largest single structures in the whole observable universe. But again, I ask you to take a look at the overall structure standing back, and it does have kind of a wave kind of feel to it, where the galaxies are and where they aren't. There's kind of these breaks of the filaments and the voids do give you some idea, suggestion that there's a wave kind of distribution going on here. And in fact, statistically, when this stuff is analyzed, this is shown to be shown to be true. And this actually is one of the predictions of our model, the model of the Big Bang that we'll be studying. So I point this out here just looking at the data. Okay, so let's look at redshift. Redshift is actually not just a concept, but it's a numerical number. And the letter that's used in cosmology is Z, little z. And no astrophysicist would use little z for any other reason than for redshift. That's how entrenched it is. It would be like trying to use little c for anything other than the speed of light. It's just not done. Some conventions are used, and it would just confuse the heck out of everybody if you start using c for some other reason than the speed of light. The same true for z. And z has a very simple definition, simple way of making numeric this idea of the redshift. And here's another um, screen. Here's another part of the presentation before, when we were looking at expansion that I've used before. So let's take a look at this again. Here we have the idea of the shifting, the redshift. Here we have the laboratory version of an absorption spectra, and we're looking at this particular absorption line here in the violet, 400 nanometers. And you look at a very distant galaxy, that line has been shifted towards the red all the way over to 530 nanometers. Tremendous shift, making the wavelengths much, much longer, shifting towards the red. And we quantified that at the time, that we actually took the difference between what we would measure in the lab of that light source and where it's showing now in the far receding galaxy, and we see the difference between those two wavelengths divided by the original wavelength, the wavelength that if the source was not moving, not far away, what it would be, and we come up with a fraction. It's a redshift, so this number will always be bigger than this number. It's always shifted towards the red. The wavelength is always longer than its original. So you get some kind of a fraction, and here is this term here that we use. It's the change in the wavelength divided by the original wavelength. Here, this original wavelength can be thought of here in terms of the lab wavelength, or it could be thought of as the wavelength that left the galaxy. When the galaxy gave off this light at whatever wavelength it is, this is the wavelength in which it started out with. So you can also think of O as the original wavelength, the wavelength when it began its journey towards us so far away, so long ago. This is its original wavelength, and here now is the wavelength that we measure, the measured wavelength, and that change divided by the original is what's going to be called simply Z. This is the redshift. And we had a nice formula at the time. This ratio here is in fact the same as the ratio of the speed of that object as it recedes divided by the speed of light. And this formula, it works very nicely when that speed is not too high, when we don't have to worry about using special and general relativity. And so that's the definition of the cosmological redshift. We know that this shift, as it gets bigger and bigger, is in fact not a Doppler effect at all, but it's actually a stretching of space-time. This is the manifestation, this redshift is a manifestation of the stretching of space-time of the actual expansion of the universe. And so the definition of Z is very straightforward. It's just that change in the wavelength from what we measure now to what the wavelength was when it left the object so long ago, so far away, that change divided by the wavelength that it left so long ago. There's the measured wavelength minus the original wavelength of when it left divided by that original wavelength. That's the definition of redshift. It's very, very straightforward. There's nothing greatly mysterious about it. Notice this number is always a positive number because this number here is always bigger. This is the longer wavelength. This is the wavelength that we now measure after the stretching of the universe compared to that original wavelength when it left. So for example, if you see something very, very far away that left with a visible light, and it was very, very far away, by the time it got to us, it'd be stretched so long, it might be in the infrared, it might be in the microwave range, how much it has been shifted towards the red. So this number here is always bigger than this number here in a redshift, and so this difference is always a positive difference. So these Z's are positive numbers. And in fact, and as I said, when Z is a modest number, just picking an arbitrary range, if Z is less than a half, then this formula does work very nice for a Doppler shift. It does give very nicely what the speed would be, that the redshift Z is simply a measure of the proportion of how fast you're going compared to the speed of light. So we get a very simple formula when z is of a modest size. The velocity of the receding galaxy is just z times the speed of light, some multiple of the speed of light. And if you remember way back then, we actually did that computation for this particular situation where we have a z of about a third, and we see that the velocity is about a third of the speed of light. This was a real surprise to us at the time because stars and close galaxies don't move anywhere near these kinds of speed. This is a speed way beyond anything that we recognize locally. This gives us our first hint that we're not dealing with the Doppler shift. We're dealing with something fundamentally different. And this is one of the things that leads us to understand that we are talking about the stretching of the fabric of space-time. Okay, so here was our graph here that we used talking about the summation of all of this redshift data of Hubble's law, that in fact the velocity of the receding is proportional to the distance, and the constant proportionality is called Hubble's constant. And here's a set of modern data in which we see the law is very well contained, particularly when the distances are not so far. They very much clump around that. As you get further and further out, there the data becomes more scattered. Here, maybe because the data is so difficult to take compared to maybe today's data, which might be more clumped together. But the point is, we had a Hubble's law, as we stated it then, that the speed is proportional to the distance. And I chose this graph to show that because it did show speed in the y-axis and distance in the x-axis as the equation reads. But if you remember, at the time, we put in redshift in that time. That redshift is equivalent to speed. It's equivalent to velocity because of this simple formula. Although this formula does not hold as z gets bigger and bigger, using the laws of general relativity, the relationship between redshift and speed does hold. It just becomes a bit more complicated than this simple proportion. So there is very much a connection, a mathematical association, a known association between redshift and speed. And we can use them interchangeably on our graphs. And in fact, we will see that redshift is more often written instead of speed on one side and distance on the other. We'll see redshift very often connected with distance, even in looking at Hubble's law. One more point about this value of z. Z can be greater than 1. Okay, z's are measured now with powerful telescopes to be 2, 3, 4. I think the largest z is around 8 that we can measure. So what does it mean when we go back to this formula? Are these galaxies receding at 8 times the speed of light? Doesn't special relativity tell us that nothing can move faster than the speed of light? Yes, but you have to make that statement more precise. Nothing can move through space faster than the speed of light. Space itself, under the laws of general relativity, they can expand as fast as they want, depending upon what we now know as some element of dark energy. So the restriction of the speed of light is the motion through space, not actually of space. And that's why these z numbers can be, in fact, greater than 1, and they are. Okay, let's take a look more carefully at this number z. Yeah, we've now quantified the stretching of the wavelength of light. Again, to get our bearings here, we have our formula, what z is. Z is defined to be this change in the wavelength, defined by the wavelength when the object originally gave out the light. And here's where we're looking at something far back in distance, far back in time, in this part of the expansion. And here's the wavelength that was sent out originally. And here's the wavelength that we see. We see it at a later time when the universe was larger in its expansion, and these wavelengths have been stretched. Okay, so again, this is not a Doppler effect. This is called a cosmological redshift. This is because of the literal stretching of space-time. So here's a kind of a good way to think about these two variables in our formula. Okay, m for the measured wavelength we see now, Zero, maybe for the original wavelength, maybe think of it as an O, as the original wavelength, the wavelength that the light was sent out at of this object that we're looking at now so far away. Do a little bit of simple mathematical manipulation here. We'll take our definition of lambda m minus lambda 0 over lambda 0. Let's divide lambda 0 into the two parts of the top, and we'll get lambda m over lambda 0 minus 1. Yeah, lambda 0 over lambda 0 is 1. Any number over itself except for 0 itself mathematically is 1. Let's bring that 1 to the other side, and we have a very interesting quantity here, z plus 1. Z plus 1, according to the algebra, is lambda m over lambda 0. If you think about this, this can be called a stretch factor. It's seeing how much the light wave has been stretched in its wavelength, lambda m, when we see it now, compared to what it was when it first left the object, the bright object that we're looking at, the object that's creating this radiation of lambda 0. It's been stretched by this factor of z plus 1. And that's exactly what astronomers call it. They call z plus 1 a stretch factor. Do one more manipulation. Let's go ahead and solve for lambda m. Just bring the lambda 0 up from the denominator up to the top on the other side of the equation. And notice what lambda m is indeed the amount of stretching that lambda 0 has gone through. That is, the original wavelength lambda 0 has been stretched, has been expanded, as the universe has been expanded by this factor of z plus 1. Notice that this number z plus 1 is always a positive number, and it's always a positive number greater than 1. Since 0 is always positive greater than 0, since z is always positive greater than 0, z plus 1 is always positive greater than 1. The expansion is always greater than the original size of the wavelength that it was when it first left that object. It is truly a stretch factor. In fact, the fabric of space-time, we know, during the time of light travel has been stretched by that factor of z plus 1. That's why the redshift looks the way it is. That's what's caused this redshift. That's what's caused the stretching of the wavelength of light. It's only because it's been traveling through space-time. So, the size of the universe from the time that the light left the source until today, we can say has been expanded by this stretch factor of z plus 1. An example, make things a bit more concrete. Suppose we're looking at a source where we measure the z of 1. Okay? It's been stretched by a factor therefore of 2. Okay? The change in wavelength has gone from 400 nanometers up to 800 nanometers, a long stretch, so that the difference between them, 800 minus 400 is 400, and 400 over the original 400 is 1. The z plus 1 number, therefore, would be 2. What that tells us is that the size of the universe today is twice the size of it was when that light from that object that we're looking at left so long ago. That's what the 2 tells us. It tells us the stretching of space-time during the time it took for the light to reach us. Okay? So just take a look at that numeric example. The more abstract sentences on the left, I think, would make more sense. So let me say it in general. In general, for a source of redshift z, a source of light, a source of radiation, and remember when I'm saying light, please, I'm not talking only about visible light. We're talking about light across any part of the spectrum, from gamma rays all the way down to radio waves. So in general, for a source of radiation of redshift that we measure z, the size of the universe today is about z plus 1 times the size at the time that the light left that source. You see these words about, I put about throughout these. That's because, it's not exactly, we're actually using the laws of general relativity. They're a bit more complicated than just these simple linear relationships we're using. But for modest z's, z's up to certainly the z's of 8 and a bit more, these numbers work out fairly well. These are pretty accurate. Given the kind of accuracy that we can get with these kinds of scales, these relationships are quite satisfactory that astrophysicists use. So that's kind of our summary here of what z can tell us about the growing size of the universe Let me read that again down the bottom right-hand side. In general, for a source of redshift z, the size of the universe today is about z plus 1 times the size of the universe at the time that light source left and began its journey towards us. Not only is it called a stretch factor, it's also called a scale factor. Matter of fact, you'll see in the readings in astronomy, astronomers will use the phrase scale factor a bit more common than the stretch factor. I don't know why, it's mathematically equivalent, so I thought we would look at them together. Let's look at this and then a few more slides, and then I'll stop and take some questions because there may be some questions here about what's going on. Again, we start with the same set of equations, and we have this definition of z plus 1 as a stretch factor. Let's mathematically do one more manipulation. Let's turn everything upside down. 1 over z plus 1 is now lambda 0 over lambda m. I've literally just inverted everything, so the equation remains valid. Now this quantity, 1 over z plus 1, is called a scale factor. That's what astronomers call this thing in terms of the changing scale of the universe. So let's see how this works. It's exactly equivalent, just we're talking about from the other side of the telescope, in a sense. Again, we do one more manipulation and solve for lambda 0. Notice that lambda 0 is the original wavelength, lambda 0, is scaled down by this factor of 1 over z plus 1. And that's where the word comes from. Lambda 0 is smaller than lambda m by this factor of z plus 1. The phrase scale factor is used. An example. Suppose we found something even further away. Well, I actually haven't gotten to that yet. I haven't quite justified that phrase yet. Suppose we find an object which measures a z of 2. That is, its stretch of wavelength is twice the size of what it would have been when it left its original source. If we measure something of a z of 2, then that scale factor would be 1 over z plus 1 would be a third. What that means is the size of the universe at the time of this object leaving at z plus 2 was only about a third of the size of the universe today. I should clarify that the universe I'm talking about here in every single case is the observable universe. Right? It is the universe that we can see, we can measure, given the finite speed of light. Okay, so again, make the general statement if I can. In general, for a source of redshift z, the size of the universe at the time the light left the source was about 1z over 1z plus 1 smaller than it is today. Okay? It's exactly the same statement as the previous slide. We're just saying it in its reciprocal way. Okay. Here's another graph that we used, very important one we used last time to look at the expanding, the accelerating expansion of the universe. This is the great data of 1998. And you can see that the graph that's used here is literally redshift is on one side and distance on the other, okay? And we had to put in, at the time I put in speed here to be the equivalent of redshift, so that we could write the Hubble's law, that we could recognize speed in the y-axis, distance in the x-axis. But in fact, the data shows is redshift. And we're comfortable with this, I hope, that redshift and speed are very much mathematically related. There is an association, a computable association between the two, and you can use them equivalently. There's one more connection we need to make now, down at the x-axis, the distance. Instead of distance, we could also use time, because we know that telescopes are time machines. The further you look back in distance, the further you're looking back in time. And measuring things in light years reminds us of that every single time. When we say something is 100 light years away, we have to remember, sometimes we forget and think of it just as a pure distance, but we have to remember when you say something is 100 light years away, we're looking at that thing as it was 100 years ago. Yeah. So if you say something is 1 billion light years away, you have to realize you're looking at that thing 1 billion light years ago. That object that we're looking at now may not even exist today. It may have blown itself up as a supernova uh, between that now and a billion years ago. The light is still coming from us at that point, and that's what we see. So telescopes are a time machine, and so not only is there an association on the y-axis that redshift and speed can be used equivalently, but distance and time can be used equivalently. And therefore, Hubble's law, here's the bottom line, guys. Here's what I've been moving to in this first part of our talk. Hubble's law is also a relationship between redshift and time. Hubble's law gives us a relationship between redshift and time. And so here it is on the left. Here's the varying different redshifts and the look back time, how far back you're looking in time. Okay. So if you're looking at something with a redshift of 0.1, you're looking at something 1,300 million light years, right? 1,000 million is a billion, right? You're looking at something 1.3 billion years ago. The look back time, how much further back in time you're looking. There's a very handy table. There's no simple formula to compute this. This is being used using the age of the universe and the laws of general relativity. They're not linear. In the beginning, by the way, this is Z here, the redshift. This is the number Z. You can see when the numbers are small, they are pretty linear. Here we go from 0.025 to 0.5. Here we double Z, and we pretty much double the look back time. But look when the numbers get bigger, going from 1 to 2. We're looking back 8 billion years. 2, no, we're not looking back 16 billion years. No, not at all. With a redshift of 2, we're looking back 10.3. You can see how these numbers very much bunch up towards the overall age of the universe. This table, I believe, is using 13.7 billion years. Here's another astronomy picture of the day, looking at the Hubble deep field, the ultra field, and looking at this tiny little patch of the sky, which you can't even see anything, even with the naked eye, but looking at it very, very closely in that patch, and finally looking even deeper than that. This is at the time, at least, whenever this was taken, maybe in around 2010, something like that. This was the largest redshift object we knew of. Had a redshift of 8.6. Okay, this thing here. Okay, we're looking in the look back time of 13.1 billion years ago. Okay, and you can see between 6 and 10, we go from 12.7 billion to 13.2 billion. Knowing this is not linear, the 8.6, they're calling it 13.1. Not bad. Okay. If we do have a universe of 13.7 billion years altogether, then this light left 600 million years after the Big Bang. 13.7 minus 13.1 is 0.6. Okay. Also interesting going on to see that the galaxy is now about 30 billion light years away. 30? It's not 13.1? It left 13.1 billion years ago. It has a redshift of 13.1 billion years. It's not 13.1 light years away? No, because over that 13.1 billion years, that's a long time, the universe has been stretching and stretching and stretching. And so now today, that object, if it still exists, the place where that object came from in the universe compared to our place in the universe is not 13.1 billion years distance, but 30 billion light years away, okay, because of the stretching of space-time. So you can see these numbers are not easy to compute. We very much have to be using general relativity to work these numbers out properly, which we, of course, have no ability to do. We'll take these numbers on faith from the astrophysicists. Okay, let's take a look here at, this is an interesting animation. Let's see if I have the bandwidth to run this. So far, so good. Hello. Let's see if we can, okay, not bad, not bad. All right. I want you to look on the left, to the simulation on the left. See if if I can get this thing. Okay, I think I did it. Not so bad. Okay, so the simulation starts here with a redshift of 10.5 and the look back time of 0.4. I'm sorry, not a look back time, but time since the Big Bang of 0.4 billion years, 400 million years. So given 13.7 is the total distance, total time of the Big Bang. If this is 4.4 billion years since the Big Bang, this would be a look back time of 13.3 billion years. So if you take a look at this 10.6 and compare it to our table, you'll see that our table works out pretty well. Here's the beginning of the of the simulation. Okay, this is very much in the spirit in which Alan asked the question at the beginning of class. If you came in early enough to hear Alan's question, he said, "How do we know where to start these simulations? Well, these simulations start so far back. How do you know how to start the thing? How do you know how much dark matter to put in? How do you know the properties of dark matter will work out?" And so this is where these simulations begin. This is about as early as we can start. Okay. 400 million years after the Big Bang. This is a number that should resonate with us. This is a big, important number. 380 billion, I'm sorry, billions and millions. 380 million years after the Big Bang is the decoupling, is the recombination, is the beginning of the cosmic microwave background. And that's where they're starting here in this simulation. At the beginning, when the cosmic microwave background has been released. And what has been released is the recombination, the atoms, the stable atoms of both regular matter and dark matter. And it begins here with, again, these simulations now can start off with a billion particles that the supercomputer can keep track of in terms of its gravitational interactions. Quite amazing what this programming can do. Notice the stellar masses here are 0. There are no stars yet. Okay, we have no formation of stars. There's been no clumping of regular matter yet here at the beginning. This is just the beginning at recombination. Okay, so let's let this thing run. If I can get this thing back here. Let's let this thing, first let me turn off the sound. Let's let this thing run. And I'm gonna, we'll watch you watch the simulation. I'm gonna watch the stellar mass until it finally registers, when we finally get the first star. If you watch the simulation, I promise I'll watch the stellar, and we'll see what we can find if I can stop this. Notice the structure is beginning to form. Okay, and here's the first place where we get the first formation of stars. And according to the simulation, it should be at a redshift of 7.5 of about 0.7 billion years. So according to the simulation, the first stars begin to form at about 700 million years. Okay? About 700 million years would be what this simulation is showing. Depending on how quick I caught, I don't think I caught this quick enough. I think you'd even catch this at 600 million years. But here we see the structure is forming, and I'll just go let this run for a bit more. What you're seeing actually is the structure of the dark matter. The dark matter actually clumps first. We won't see the regular matter clump until you start to see the yellow. There it goes. There's the yellow, pink, whatever, pink, I guess. There's the regular stars and galaxies. These are all galaxies, by the way, beginning to form. We're looking on the left. The right is something different. Okay. You see the structure isn't changing all that much. Where are we here? We're at 2.4 billion years after the Big Bang. The structure, guys, here is pretty much cooked. Yeah, although we've got 11 billion years to go, this is not going to fundamentally change anymore. Okay, it's going to get thicker, more regular matter will fall into the dark matter and become what we see, what we've been studying for the first 2,000, for the first 5,000 years of civilization. Only in the last 20 years have we studied anything else. What we see begins to form more and more, but the overall structure is determined by the dark matter, and it's not going to change all that much. Okay? Again, I would like you to play with this if you can, if you get a chance at some point, and compare the time after the Big Bang. From there, you'll have to subtract from 13.7 to get the look back time, and compare the look back time to the redshifts that they're showing here in the simulation, you'll see that they work pretty well according to our table. Our table is pretty good. You can see where our stellar masses are, 7 billion solar masses. We're starting to get galaxies here beginning to form, proto-galaxies. And we'll just let this run a bit more. See, the redshift is going down. Time after the Big Bang is going up. The connection of redshift and time. And although this simulation, they're turning it for us, so we get a three-dimensional view of it, I think you can agree with me that the overall structure is not fundamentally changing. This is an important point that the model is going to predict, and these simulations do show. Okay, you can see that the pink is growing thicker and thicker. This is the atoms. This is the normal matter, which is the fusion of hydrogen burning the stars that we see. And finally here we're getting around to about a redshift of 1. We see we're 6.5 billion years after the Big Bang, and so on. Okay, so I encourage you to look at this. This is a beautiful simulation. This is the illustrious people. These are the gold standard of the simulation groups, and they're very, very well regarded. In the Wednesday email, I gave you an email to talk about these people and kind of the work that they do, and another simulation from another group. Okay, so that was the point I wanted to make. I'm going to close this down to save my bandwidth. I want to close down the whole Zoom. I think that'll cut us off. Oh, yeah, I almost closed the whole web. Oh, yeah. Okay, I think I did that. All right, let me minimize this. Can I get myself back? Am I back? I think I'm back. All right, I'm back. All right, Greg, do we have any questions?
Yes, we do, Peter. 2 questions. First question from Joe Parisi. Regarding redshift, how do you measure / observe the initial wavelength of the distance galaxy, ... to then compare to the final wavelength?
That's a very good question. Okay, you have to know what you're looking at, and you have to have some semblance of what is the radiation that's coming off of that object. So when you're looking at something very, very far away, and you're looking, for example, at a quasar, what you do is you look at close quasars, and there are close quasars. There are quasars that are not in our galaxies, but they're in, for example, the Andromeda galaxy. So you look at something which is of the same type, which is very close, which we can analyze the light without any kind of significant redshift. And that's how we can tell what that light should have been when it left back long, long ago. That's a very good question. That's a question which I did not mention at all, and that's a very important, obvious. It's an obvious hole in my explanation. So, Joe, thank you very much for that very excellent question, helping me complete my explanation. Next question.
This is from Alan and 7. Z is a ratio of wavelengths for some particular feature in the spectrum. What line is selected for this calculation? This is important to specify because the apparent Z changes through the spectrum, since the spectrum of a very distant source is both redshifted and squeezed in length.
Really doesn't matter what wavelength you talk about because they're all being stretched by the same amount. So, for example, one wavelength to use would be the brightest. These are all basically black body spectrums. Okay, all these objects are fundamentally of a black body spectrum. So one very convenient wavelength would be the brightest wavelength to use. You use the brightest wavelength as you think left source and its brightest wavelength at that stretched wavelength of now. Okay, so let us continue on here. So we have this relationship now between distance and the redshift. Here's that Sloan survey. Here's the BOSS survey, which just finished up this year. And notice that the distance, they aren't even showing distances. They're just showing redshifts, okay? You're supposed to know that these redshifts are associated with distances. And of course, we're using our table. we could mentally put them in if we like to get an idea of just what kind of distances they're talking about in this survey. Here, we're here looking out from our telescope, looking out into the universe here in this sector of the sky. Here's another one where, again, this is another part of BOSS where they're just showing the redshift um, at all. And here's a word that we want to become comfortable with. This is the Baryon Oscillation Spectroscopic Survey. What is that? We need to build a little vocabulary of our particle physics to complete the physics behind our cosmology. We'll be getting to that today, hopefully. And here again, just to look at our table, here's something with a redshift of 0.7, and that is something which is a 6.5 billion years ago. So that when the quasar is, I'm sorry, what am I reading? I'm sorry. The redshift of 0.7 is associated with 6.5 billion years ago, look back time. And again, if you look at the table, our table is pretty good. Just trying to give you confidence in the table that this independent data does comport with our redshift look back time table. And here's a very short video, which I won't play, of the BOSS stuff, but here they're just showing look back time. This video is part of the larger video in the Wednesday email. Please play this if you get a chance. I think it's less than a minute long. But here I just wanted to show an example where what they're showing here is just look back time, and not showing distance at all. But again, from our table, you could mentally put in the various different redshifts. And I show this to remind you how these redshifts create very, very large distances very quickly. Okay, this is just a redshift of 4, which, well, I don't know, 4 doesn't sound like a big number, and no, and it's not in certain senses. But in terms of look back time, it's the vast majority of the time of the universe, a redshift of 4. Redshifts of 4 are things which are very, very, very far away. We're looking back very, very deeply in time. Okay, and one more look at the kind of a snapshot view of one of these simulations. Here's a simulation, I think, from another group, third group from the University of Chicago group. And notice they're just showing Z's. They're not showing times, they're not showing look back times, they're not showing how far away these things would be in the universe from us now. They're just simply showing the Z's. So again, this concept of the redshift is fundamental. It's used in astronomy and in cosmology. You're just supposed to know what these things are and what they mean. And again, using our table, we could mentally put back how much time has elapsed since the Big Bang. Right? These are numbers since the Big Bang. These are the reciprocals of the look back times, using 13.7 as the total time of the age of the universe. And these simulations go on and on and on. And where does the sun come in, the formation of the sun? Only the next to last one. Okay? So we're very much a Johnny come lately in this story of the age of the universe. If there was one picture that I would like you to hold about the chronology of the universe, this is not a bad one to start with. Okay, there are many, many of these out on the web, as you probably know. But here's a relatively simple one. And, oh no, I'm sorry. I've mentally run ahead of myself. I want to do one fun thing now with this redshift. Yeah, this is like my favorite slide of the presentation. I get to do a little bit of math with you. This is fun. Here is, of course, the chronology of the expanding universe in time. Here it is in time, and here it is in degrees. As it expands, it gets cooler and cooler. Here is a demarcation, guys, that I really want everybody to know, everyone to be comfortable with. This is recombination and decoupling, okay? 380,000 years after the Big Bang, where the temperature was 3,000 degrees. This is the microwave, cosmic microwave background. This is when it is released. And this is a light. This is a radiation. This is the furthest radiation we can see. And it has a Z. It has a redshift. And let's go ahead and compute that redshift, okay? And that redshift has a scale factor. It has a stretch factor. And we can actually measure the size of the universe compared to now when the cosmic microwave background was released so long ago, so far away. Okay, this is a fun calculation, and it's not difficult. It uses all the stuff that we know. The math is not hard, and even for you non-math types, I think you'll follow this. This is fun. Okay, so I start with our general statement of what we've learned about the scale factor. In general, for a source of redshift Z, the size of the universe at the time the light left the source is about 1 over Z plus 1 smaller than today. And that's what we're going for. If we can figure out Z, we can figure out Z plus 1, we can figure out 1 over Z plus 1, and we can make a statement about the size of the observable universe at the time the cosmic microwave background was freed compared to the size of the observable universe today. That's pretty cool if we actually can make such an intelligent statement. And we can. Okay. So let's calculate the approximate redshift at the decoupling at the temperature of 3,000 degrees. I'm using the word approximate and about again, guys, because I don't want you to take these numbers completely seriously to the 5th decimal place, okay? We're not working in that kind of scale, okay? We are working in approximations, but very reasonable and very acceptable approximations, given the scale that we're talking about, okay? For example, you'll hear that the decoupling is 380,000 years after the Big Bang. You'll often see it rounded to 400,000 years after the Big Bang. You know, compared to 13.7 billion, 380,000 compared to 400,000, it's not a big percentage difference, okay? In fact, this number is known to this kind of accuracy within the model, but you'll see people round it off, and scientists round this thing off, not taking these numbers so seriously. This number of 3,000 can't be taken to any kind of decimal place. It's about 3,000 when this event took place. Okay. So we have Z. Z is lambda m over lambda 0 minus 1. Okay, that's Z. We need to know what these lambdas are. So let's use Wien's law. Let's go ahead and take Alan's question. Let's go ahead and use the brightest wavelength. Let's use the brightest radiation that's coming from the microwave background. Let's use that and see how that stretches, because they all stretch by the same proportion, because they're all traveling through the same space-time. Okay, so when the light left, when the cosmic microwave background left at 3,000 degrees, it had a brightest in its black body spectrum. We calculated this before, of 1 micron, right? 0.1 centimeters, 1 millimeter. Okay. Now we have a temperature of about 3. So now that light has been stretched to about 1,000 microns, much longer. And there's the stretch factor right there, 1,000. There's our answer. Okay. The universe back then was 1,000th of the size it is now. Or our universe, our observable universe now is 1,000 times bigger than it was back when the cosmic microwave radiation was released. And you'll see numbers of 1,000. You'll see more precise numbers of 1,089, because in fact you are allowed to use that kind of precision under certain models. You'll see the number bounce around. 1,000 is good enough for us. Just to finish off the math, if Z is equal to this number of 1,000 over 1 minus 1, so the actual Z number, the actual redshift number of the cosmic microwave background is 999. Z plus 1 is 1,000. Okay, so you can see these numbers don't change very much when Z is so large. But notice how large Z is. Okay, you can't be using the speed of simply Z times the speed of light. Okay, that just simply won't work. These numbers are too big. But after all is said and done, the scale factor is 1 over 1,000, which we saw immediately with the 2 wavelength computations, And we can conclude a very interesting fact, that at the time of decoupling and recombination, about 380,000 years after the Big Bang, the observable universe was about 1,000th the size that it is now. Think about the fact that we can say that we have a theory that gives us confidence that this is true. I mean, we know a lot of things in science which we can't observe directly. This is a big one. We're talking about something which is 13.4 billion years ago. We're talking about the size of the observable universe, and we can say it with confidence. This is kind of a measure of how far the science of cosmology has come in 100 years. If you were to give a statement like this to anyone before that, they would look at you and just laugh. A scientist, and look, never mind a layperson. You see, there's no way you could ever possibly know that, even with the latest 19th century science, even with knowing about special relativity and quantum. There's no way to know something like this. What is it that allows us to make statements like this? Well, we're coming to the theory of the Big Bang, which puts all this into context. We're getting there. All right. So one more old slide, the slide of the age of the universe. We did this back where we used Hubble's law to show that 1 over h was a time, and that time was approximately the age of the universe, and we calculated that at that time to be 13.8, 13.8, 13.7 between friends. Is there a big difference when you're talking about 13 billion? No, not really. Take your pick. If I think I've been using more consistently here in these tables, etc., 13.7. All right. So I want to show you one of these, things that are out on the web. They're all over the place. If you took 13.7 billion years and you compressed them into 1 year, what are we talking about? And just, I want you to just take a look at this slide at your leisure. What it shows, okay, what I really think this shows is that we have no conception of what 13.7 billion years really means. It is beyond our understanding. Because when you look at this, when you see that if you took 13.7 billion years and compressed it into 1 year, okay, you wouldn't even begin to talk about the dinosaurs, until, December. And the dinosaurs are like a long, long way away in time. You wouldn't be able to talk about historical times where we have any kind of written record, or even the time when agriculture began, in the archaeological findings, for example, of the city of Jericho, where we find the first semblance of some kind of agriculture. Sorry, I may have said architecture, of agriculture, the earliest signs of some kind of civilization as we understand it. That wouldn't happen until the last second of this one. What it means is that we really have no comprehension of how long a time we're talking about. And that's the only reason why. It's a very interesting slide. It's worth taking a look at. But my point is to be more of undermining if you think you understand what 13.7 billion years really means to us in kind of a visceral kind of way. So sorry to be so subversive. All right. Here's the picture that I wanted to say, that if there was one model, one picture of the Big Bang that I'd like you to hold in your head, this is not a bad one. I've doctored it up a little bit. But I found this one on the web. It has some information, but not too much. These things vary all over the map. Here's one where it hits some of the real high points, particularly after I've doctored it up a little bit. We start with the Big Bang, some beginning, time 0, I guess. And the model says it begins with this period of inflation, where the expansion, you can see, is very, very great, tremendously accelerating expansion, much, much greater than this kind of expansion here after the inflation period is over. And you see it ends very, very quickly at 10 to the minus 33 seconds. This is a ridiculous number. Okay, this is another number that we have no conception of. Okay, What is 10 to the minus 33? Well, 10 to the minus 12 is a trillionth. So 10 to the minus 24th is a trillionth of a trillion. So from 24 to 32 is what? Is 11. That's 100 billionth. So this time is 100 billionth of a trillionth of a trillionth of a second. It's ridiculous. We have no notion of what this means. It comes from the theory. It comes from our understanding of quantum theory. It's not a number which is just pulled out of a hat. But is it 10? Is it 10 to the minus 33? Is it maybe 10 to the minus 34? Is it 10 to the minus 32? That we can't take these numbers too seriously. But it is in this kind of order of magnitude of when we know that the inflation should have ended, if we see where the universe has gone from there. And these are all deductions that we're making within a theory. Okay, so from when inflation starts and the regular expansion begins, we have the matter and energy as we understand it begin to form. Finally, nuclei begin to form, protons and neutrons. Finally, the recombination finally forms. We get stable, I'm sorry, atoms, nuclei of even helium and deuterium form, all within this period from the end of inflation up to that 380,000 years when the cosmic microwave background is released. Okay, right there, recombination and decoupling. We finally get to that point. The atoms become stable. The few atoms, the few types of atoms that are there, mostly hydrogen and helium, and the cosmic microwave background is released. And we then go in what's called the dark age. When the cosmic microwave background is released, if you look at the spectrum, okay, if there were eyes to see it, that light is partly in the visual spectrum. It's a deep orange-red color. Most of it is in the infrared range and even microwave range. That's why it's called the cosmic microwave background, because it was first discovered right in 1964 by Penzias and Wilson in the microwave range, and so that name stuck. But actually, most of the light is actually in the infrared. But there's even a little bit in the red and the orange. Okay, so when it was first released, you could see it if you were there. But it soon begins to cool because of this expansion, because this space-time is stretching wider and wider, larger and larger, and any gas, which is what this is modeled on, of this plasma, these atoms, as they expand, they will cool. And quickly then this radiation will be stretched into wavelengths that we do not see, okay? And there's no stars yet, and so this is called the dark age, okay, where there's no visible light in the universe until the first stars form, the first fusion that we get. It's a long time, from 380,000 years to about 300 million, 400 million years, somewhere in that neighborhood where the first stars appear. So the dark age is also a period that, and then the first stars appear somewhere 300, 400, 500 million years. And then finally the clumping of those forming stars begin to form what we could recognize as galaxies. And then the clusters of galaxies and on and on. Okay? And here's just to show in scale some way, some kind of context, not in scale certainly, but in context. Here's the formation of our sun, way, way out here. So this is not a bad picture to kind of stare out and say, I understand that we've got inflation, we got the cosmic microwave background, we've got the dark ages, I kind of know what that means. We got the stars forming, we got the galaxies forming. Not a bad picture. As you could do a lot worse if you had a fundamental understanding that you want to explain to your 9-year-old grandchild. This might not be a bad way to start. Talk about the expansion of the expanding and evolving universe. Here's a more complicated one, a more sophisticated one, and this is one that's very favored by scientists, astronomers, and astrophysicists who give talks. As you can imagine, I've seen a lot of talks on YouTube. I've watched a lot in preparing for our class. And finally, it's time to give this model, this theory of Big Bang, a name. And it's called the lambda cold dark matter model. That's a mouthful. It's even summarized into lambda. This is the capital Greek letter L, and CDM model. Lambda, of course, we recognize as the variable that's used for dark energy. This is the cosmological constant. So the cosmological constant is clearly a key piece of this theory. We assume that dark energy does exist and it is driving this expansion. It's part of our theory. There are other theories, but our theory has lambda in it. And then it has dark matter. And the dark matter is cold. Okay? Why it's cold as opposed to hot, I'll explain in a bit. But that, at any rate, is the name of the model that we're studying. This is the traditional model of the Big Bang. This is the one where most astronomers ascribe to, feeling that this is the best model we have right now. And the cosmologists who are working on modifications to this model and even alternate models are in a minority. Doesn't all mean that they're wrong. Not at all. Not at all. They're working on true outstanding questions, true outstanding problems that can't be answered right now. They're looking at viable alternatives. Give theorists a model and they'll tinker with it. Give them a chance and they'll tinker it to death. Particularly if you've got some data which doesn't completely agree with the theory. But a few extra things which are here in this picture. We've got the notion of quantum fluctuations. Okay, a very important idea. Actually before inflation, and then inflation takes these quantum fluctuations and blows them up. Here's at 400,000 years. They've rounded it up. This is the afterglow. This is the cosmic microwave background. If you know 3 letters at all, one acronym in cosmology, please recognize CMB. That's the cosmic microwave background. We've got the dark ages, we've got the first stars, we've got the development of et cetera, okay? They even kind of show you the accelerating expansion here. It kind of swoops up a little bit. And an overall timeline, okay? So this is kind of the next level of picture that one can have in one's mind to put this evolution in a context for yourself, okay? All right, we only have 5 minutes, so let us finish up with the true overview of this model. 3 important slides I want to get to. First of all, what I've claimed is what I've hoped to have done in the first 5 classes is to give the lay of the land. What does the universe look like now? Well, this model, the lambda CDM model, should account for the things that we've discovered about what the universe looks like today. And what are they? What are the large overall cosmological features of the universe? We must always start with the expansion of the universe. Second, right on its heels is the cosmological principle that on its largest scale, the universe is homogeneous and isotropic. It basically looks the same, no matter where you are and no matter what direction you look at from wherever you are. At its largest scale, the universe is like Jello. Okay? No, of course, it's not at all Jello on smaller scales. The filaments and voids show that at a pretty large scale. But if you step back even further from that, at redshifts even bigger than that, it looks homogeneous and isotropic. On the largest scale, the geometry of the universe is flat. I know some of you may still be struggling with this idea of the geometry of the universe because, first of all, well, it's 3-dimensional and we think more of geometry as 2-dimensional. It's worse than that, right? The geometry of the universe is 4-dimensional. Right? We have space-time. So we're talking about a 4-dimensional geometry, not a 2-dimensional geometry. Give us a chance in the next lecture to talk a little bit more about the geometry of the universe as we look at the evidence for it in a bit more detail. So let's hold our questions about the geometry of the universe being flat. But it's a very, very important property that we have discovered empirically about the universe, which is borne out in this model. It is predicted in this model. We observe the abundance of the primordial hydrogen, deuterium, and helium. This is something that we've not talked about a bit, something I've not gotten a chance to mention, okay? That we do have measurements of how much primordial hydrogen and helium there is, which is primarily all there is. The deuterium and a little bit of lithium Aronian traces. Where do we see this primordial hydrogen helium? In the voids, okay? That's where the primordial gas is. Hasn't coagulated into any kind of stars. It's still out there, presumably the way it was the beginning of the Big Bang, beginning of recombination, when it was just spread out in space. It never did clump together, never did find any dark matter to clump near, and it's basically the way it's been for 13.4 billion years. And when we measure that gas, we find exactly the distribution, how much of it is helium, how much of it is hydrogen. Yeah, it matches our model. We'll be looking at this in great detail. This is one of the strongest pieces of evidence for the Big Bang, the model of the Big Bang, okay? Probably the biggest single piece of evidence is the existence and the structure of the cosmic microwave background. First of all, its existence, the fact that it was predicted and found finally in 1965. And its structure, we've begun to look at its structure, those clumping, the sizes of the clumping, which is the evidence to show that the universe has a flat geometry. We've only begun to look at this. We'll be looking at this very, very carefully next time. Large-scale structure, distribution of the galaxies, that was all of what Lecture 2 was all about. And finally, the changing rate of expansion. The currently expansion is now accelerating. That, of course, is the story of dark energy. Okay. What are the fundamental assumptions of our model? What's behind the model? There come in two groups. One is general relativity. We assume that general relativity is the correct theory of gravity. We assume that dark energy is a manifestation of a component of the theory of general relativity. Okay, that this the non-zero cosmological constant, this concept, this quantitative concept within the theory, is what dark energy is. May not be that, but that's what our model, that's what our theory is assuming. These are the fundamental assumptions. You have to give me these assumptions so I can explain the theory. We'll talk about disagreeing with the theory on the last class, but allow me to explain the model as it now stands. And the model does explain dark energy as the cosmological constant of the theory of general relativity. The other two come from quantum theory. And we're going to have a little bit of look at smallest look at some of quantum theory, so that just the quantum theory of matter, just so that we have the right vocabulary that we can use. But the two basic assumptions is that quantum theory and the standard model of elementary particles is the correct theory of matter and energy and forces on the smallest scale of the universe. We're going to use this theory. We're going to assume it's true. And this is the pillar of modern physics. So yeah, you would think that the standard model of astrophysics would use the standard model of particle physics. And the last one is, and this is a big one again, may not be so, but we're assuming that dark matter is yet an undiscovered cold, slow-moving, that's what cold is getting after, particle, that upon its discovery will find its place in the standard model. We're assuming that. Okay, guys, we're assuming that. Dark matter may not be in the standard. It may be something totally different that we have no understanding of, that we have no understanding truly of gravity, and therefore the top assumptions are wrong, and that's why dark matter deals with gravity, but these are the assumptions that you have to allow me to make so I can explain the theory. And finally, the evidence. Okay, some of this we've seen in a small scale, some of this we've not. Let me just run through this, because this will set the tone for our next class, going through the theory itself. The expansion of the universe according to Hubble's law, the calculation of this abundance of 75% hydrogen, 25% helium, the prediction of the cosmic microwave background, the calculation of its black body spectrum, the density fluctuation characteristics, which we have a lot to say about, okay? The density fluctuations of the CMB will go into the density fluctuations of the scale of the universe. Those are those waves I was trying to get you to see, whether you could see them or not in the Sloan survey, okay? The fluctuations of the cosmic microwave background flow into, create the structures of the voids and the filaments. Okay, the polarization of the cosmic microwave background tells us something very important. Haven't mentioned that at all. And finally, the supercomputer simulations. These simulations begin with the assumptions of our model. That's where they start. So the fact that they're successful to that degree supports the cosmic microwave background. I'm sorry, it supports our model. So we'll stop here. We have a few more things to say in the slides, as you see. We'll finish that next time and then go into some of the details of this model of the Big Bang. All right. If anybody is still with me, I'm sorry to go over, but Greg, do we have any outstanding questions?
Yes, we have two questions. The first one is from Gwen. Any theory about what the universe might look like 5 to 10 billion years from now?
Oh yes, we will definitely talk about that in our last class, for sure. That's a nice topic to talk about. Once we understand the model of how we've evolved up to here, where's it going from here is a natural question, and we'll very much look at that.
And the last question is from Brad Roscoe. Everything is based on Hubble constant being constant, and yet the data shows it is not, especially at early times. It could
You're
even,
absolutely right that the Hubble, I'm sorry, did you not finish? I'm sorry.
finishing up, it could even be much more different at even earlier times, closer to the Big Bang. This cold definitely affects the model. This could definitely affect the model.
It definitely, you're absolutely right, Brett. It definitely affects the model. And this model does not assume that the Hubble constant is a constant. The Hubble constant is a misnomer. And one of the things you'll read in the, if you're reading a book on cosmology, for us, the intelligent layman, that's one of the things they love to point out, that the Hubble constant is misnamed. It is not a constant. And the changing value of the Hubble parameter, as is what's really properly called, is accounted for in our model. We're not being so naive. When we do that calculation of the age of the universe of 13.7, 13.8, yes, we are using the Hubble constant, the Hubble value to be constant, but that is just an approximate number. It turns out when you do all the bells and whistles and do it very, very carefully, it is amazing with the slowing down and the speeding up and the this and the that. It turns out to be 13.7, 13.8 all over again. So that very simple calculation that we use is actually a good one to show at our level of exposition. But we are the model is very cognizant of what you very well point out, that the changing value of the Hubble parameter very much will affect what's going on in the structural development of the universe. All right, guys, I'm sorry to keep you over. I try not to do that, but I did want to finish up in a natural place. Have a good week, everyone.
Thank you, Peter.
Okay, I'm going to close.
Thank you so much.
Okay, I'm going to close up here. Stop the recordings, the first thing.